Here are the notes for section 3.2, Coulomb's law in one dimension. In the last section, we looked at electric force caused by charges, like and unlike charges, positive and negative. Now what we're going to do is we're going to quantify those forces. So Coulomb's law allows us to actually determine the force between two charged objects, Q1 and Q2, separated by a distance. And Coulomb's law is this. The force is equal to K times Q1 times Q2 over R squared, where K is 8.9875 times 10 to the ninth. I usually simplify K to be 9 times 10 to the ninth Newton meter squared per Coulomb squared. Now, technically, K comes from a concept of something called vacuum permittivity, which has to do with how easy it is for a spark to jump across two charged plates. And we'll be talking about that more in section 7 of this unit when we talk about capacitors. But for now, it might be helpful to know, or just kind of have a heads up, that K is based on a number called the vacuum permittivity, which is 8.85 times 10 to the negative 12th. And it's actually, K is equal to 1 over 4 pi times that vacuum permittivity. Anyway, for now, when we use Coulomb's law, we'll just be using 9 times 10 to the ninth for K. Okay, so let's look at an example. Example 1, object A has a charge of 2 microcoulombs and object B has a charge of 6 microcoulombs. Which statement is true? Now, first of all, just for kicks, I'm going to actually plug this into Coulomb's law. So I've got K, I've got Q1. I'd like you to notice that micro means times 10 to the negative 6th. And then I've got 6 microcoulombs for charge B. The signs of the charges are going to tell you if it attracts or repels. So you just need to remember that like charges are going to repel. So if I had drawn these out, I would know that these two charges would repel, and I would draw a picture to determine the direction of the force. Anyway, I could use this formula to determine the force. I don't have the radius, which is a problem. But it turns out that it doesn't matter because Newton's third law still applies here. The force of charge A on charge B is going to be equal and opposite to the force of charge B on charge A. And therefore, choice B is the correct answer to example 1. Example 1 turned out to be really a question about Newton's third law. Okay, let's look at another example. 2 styrofoam balls of mass 10 grams are suspended by threads of length 25 centimeters. The balls are charged, after which they hang apart, each at an angle of 15 degrees to the vertical. So I've drawn a picture of this, and I've used trigonometry to figure out half the distance, or the distance to this midline. And I figured out that it's 6.47 centimeters. If I double it, it's 12.94 centimeters, or 0.1294 meters. I'm going to need that distance to use Coulomb's law. Okay, so let's look at the questions here. Are the signs of the charges the same or opposite? I know the signs must be the same because these are repelling. Are the magnitudes of the charges the same? I would say no, because the force of 1 on 2 is equal and opposite to the force of 2 on 1 by Newton's third law, even if the charges are different. So Newton's third law holds even if the charges are different. Part C, find the net charge on each ball, assuming the charges are equal. So what I'm going to do is take the ball on the left here, and I'm going to draw a force diagram for it. And so I've got 3 forces. I've got the force of gravity, I've got the electric force, and I've got a tension force. And these 3 forces must sum to 0, meaning that this electric force is equal to the horizontal component of the tension, and this gravitational force is equal to the vertical component of the tension. Then the tangent of the angle is equal to the opposite side over the adjacent side, and the opposite side is FE, and the adjacent side is FG. So I'm going to solve for FE, and I get 0.026 newtons. And now I can take this 0.026 newtons and I can plug it into to Coulomb's law and solve for Q. Since Q1 and Q2 are the same, I can rewrite the product of those numbers as Q squared. I've got my R, my distance between the charged balls here, as 0.1294. And when I solve this, I'll get 2.2 times 10 to the negative 7th coulombs. What would happen if the balls were uncharged? They would not repel. They would just hang there, kind of like we practiced in the sticky tape lab with paper. There's a special name for these lightweight styrofoam balls. They're called Pith Balls, and they're used in lots of physics experiments to see what happens with charged objects. Let's look at example 3. Two charges, Q and 3Q, are separated by a distance d. Where should a third charge be placed so that the net force on it is 0? So I've drawn a picture of this here. I've got Q on the left, and I've got 3Q on the right, and they're separated by a distance d. So here's d. So then what I'm going to do is I'm going to put point P somewhere in the middle, and I'm going to write out those distances. So the distance on the left I'll call x, and the distance on the right will be d minus x. Now what I can do is I can use Coulomb's law between Q and P, and then I can do it again for P and 3Q, and I'm going to set those equal to each other. So here's what that would look like. Between Q and P, I've got K, Q, little q. I decided to call this little q. Right there. There's my little q. K, big Q, little q over x squared equals K, 3Q, little q over d minus x squared. And now it's an algebra problem. So I canceled the k's, canceled the q's, end up with 1 over x squared. Here I am here. 1 over x squared equals 3 over d minus x squared, quantity squared. Then I cross-multiplied, and then I simplified to make a quadratic equation. And now the big idea here is that we would solve this with a quadratic formula. We don't know what d is, so we don't have a numerical answer, but we could plug into the quadratic formula to solve it. All right, those are your notes for section 3.2. Hope that made sense, and please reach out if it didn't. I'll see you in class.